Start. Start. Good evening, everyone, and welcome to the fifth Dr. Arvind Bhatnagar Memorial Lecture and the 112th Pyalka Amrut Vyakhyan. It gives me immense joy to welcome our speaker and guest of honor, Dr. Frank Hill, Senior Scientist Emeritus from the National Solar Observatory in the US, to deliver today's memorial lecture. Before we begin with Dr. Hill's presentation, I would like to say a few words on the importance and significance of today's memorial lecture. The Udaipur Solar Observatory was founded in 1975 under the vision and leadership of Dr. Arvind Bhatnagar. Dr. Bhatnagar was born in Biawar, Rajasthan on 19th November 1936. After completing his MSc in physics, he joined the Uttar Pradesh State Observatory Nainital in 1958 and worked there until 1961. He obtained his PhD in solar physics in 1964 from Agra University while working at the Kodaikanal Solar Observatory under the guidance of Professor Vainu Bappu. He was awarded the prestigious Carnegie Fellowship to work at the Mount Wilson and Palomar observatories in the US from 1968 to 1970. He also worked as a resident astronomer at the Big Bear Solar Observatory of the California Institute of Technology in Pasadena, California until 1972. Dr. Bhatnagar returned to India to establish the Island Solar Observatory in Udaipur's Fateh Sagar Lake, which was initially managed by the Ved-Shala Trust in Ahmedabad. His efforts were instrumental in USO becoming a part of the Physical Research Laboratory or PRL in 1981 and has emerged as a leading center for solar physics in the country and the world. The last 40 years have witnessed a phenomenal transformation of the facility. In 1995, USOPRL became a part of the prestigious Global Oscillation Network Group or GONG, a flagship synoptic program of the National Solar Observatory to study the internal structure of the sun, with Dr. Frank Hill playing a major role in the inception, establishment, and operations of the GONG program. In 2015, the 50 centimeter multi-application solar telescope or MUST was installed at the island site of USOPRL, making it a state-of-the-art facility to study the sun with high spatial and temporal resolution. The memorial lecture is dedicated to the memory of the late Dr. Arvind Bhatnagar, the founder of USO, and for his important contributions to solar physics in India. The memorial lecture is aimed at commemorating the rich history and growth of USOPRL and is organized every year in the month of November, close to the birth date of Dr. Bhatnagar. The lecture is delivered by a senior solar physicist from India or abroad with vast experience in theory, observations, or instrumentation development, which has paved the way for the future of solar physics in the 21st century. The Dr. Arvind Bhatnagar Memorial Lecture was initiated in 2021 during the Platinum Jubilee year of PRL, as well as India's independence, and is arranged as one of the special lectures in the PRL Ka Amrit Vyakhyan series. I now request Dr. Shibu Matthew to introduce our guest of honor, Dr. Frank Hill, to the audience and invite him to deliver the fifth Arvind Bhatnagar Memorial Lecture. Thank you.
I think most of the people working in solar physics doesn't need any introduction to Professor Frank Hill. But as a formality, just I want to say a few words. So, Dr. Frank Hill was a scientific member of the National Solar Observatory, USA, from its founding days, actually, I think in 1983, until his retirement in 2020 as an emeritus scientist. At NSO, he served in several important positions. He worked with the NSF Global Oscillation Network Group program, in 1984 and carried out important roles including site survey scientist, as a site survey scientist, deployment team leaders, data scientist, and director of Gong program. So Dr. Hill had held several key scientific positions and leadership roles in major national and international solar programs, including Global Oscillation Network Group and the NSO Integrated Scientific Program called NISP. He led the deployment of a team that installed the Gong instrument in Udaipur, and he is having a major role in putting Udaipur solar observatory on the world map by bringing the Gong instrument to Udaipur. During his illustrious scientific career, he has been instrumental in substantially advancing the understanding of the coupling of solar interior dynamics, surface magnetism, and space weather relevant solar variability, while also strengthening long-term data infrastructure essential for predictive solar physics. His work has been published in more than 500 scientific papers. He is the recipient of Aura Service Award for his outstanding and dedicated service to the solar community through his work with Gong and NSO Digital Library. So with these words, I welcome Professor Frankel for telling us the talk.
Thank you, Shibu. Thank you very much for that glowing introduction, of only half of which I might believe. So hello, everybody. Welcome to the talk. This will be a talk about how the sun rotates and why we should care about it. I hope you enjoy it, and I hope you learn things along the way. Let's see, where's the clicker? Okay. Yeah. Can you hear me? Can everybody hear me? Yes, good, okay, thank you. Okay, so I don't know how many of you are familiar with American soap operas, but we have one long-running one called as The World Turns. So I decided to call this talk as The Plasma Turns. And it's about the rotation of the sun. I'm going to give you a brief introduction to solar physics and the structure of the sun, and a number of other topics: helioseismology, astroseismology, exoplanet habitability, and space weather along the way. So it'll be a wide range of topics. Oops. To move forward. Okay. Okay, so why do we care about the sun? Well, as you probably know, it's a source of energy for just about all the life on Earth. There are some geothermal vents deep in the deep ocean that never see the sun, but they get their warmth and energy from warm water coming out of the vents below. But for the rest of us, which is, well, most of us, it's the sun that creates the energy, heat, and light for us. It can also create problems with our technology today. Your cell phones, your GPS systems, radio communications, and things like that. That's called space weather. And it is vital for astrophysics. It's the closest star. It's the only one that we can observe in detail. And so that means a lot of things are derived from the sun that are then applied to other stars. Thank you. There we go. So this is the structure of the sun. Let's see, this is a pointer also? Yes, okay. Here's the sun with a quadrant of it cut away. At the very core is where nuclear fusion occurs, and that is the production of all the energy and light that we eventually receive on Earth. It takes 100,000 years for a photon that's generated down here to finally get to the surface and get to us. That's for an individual photon. The energy is transported out in this area by radiation in the radiative zone, so it's transported by the emission and absorption of photons. And then when it hits about 70% of the way out, we enter the convection zone, where the energy is transported by the actual motion of material, like the boiling in your kettle when you make your tea. That's convection. This is convection in the sun. There's a number of things on the surface of the sun that we will, some of which we will talk about, not all of them. In particular, we'll talk about sunspots. There are also subsurface flows that occur that are very important for determining how the sun behaves. The convection occurs when the temperature gradient gets very steep inside the sun. At the surface, the sun emits a whole very wide range of wavelengths of light. Here, we show several different wavelengths. The colors are all added by computer people. But you can see some things, some of the wavelengths of light, you can see features that you cannot see in other wavelengths. So we use all the different wavelengths of light to learn about the surface of the sun and also the interior of the sun as well. Of all these wavelengths, there are a couple that are not good for us. One is X-rays. Of course, you know about X-rays when you go to the doctor. Too much exposure to X-rays is not good for you, nor is too much exposure to ultraviolet light. So this is a picture of the sun in X-rays and a picture of the sun in ultraviolet. Again, the colors have been added by a computer program. So now why do we care about the rotation of the sun? Now that you know a little bit about the sun itself. Well, the sun has a magnetic field and it has sunspots. All those are generated by the fact that the sun rotates. It generates the solar cycle, the cycle of sunspots that occur over an 11-year period, which we'll go into. It creates the space weather that impacts us on Earth. Again, all stems from the rotation of the sun. Rotation of the stars can impact whether an exoplanet in another stellar system is habitable or not. And it has implications for the evolution of stars. How fast a star rotates will affect how it evolves, how it changes over its lifetimes as well. So these are a number of very important reasons why we need to study solar rotation. So let's talk a little bit about sunspots here. They are dark areas on the solar surface, which is called the photosphere. Here in this picture of the sun, these are sunspots here. They're here at Udapar Solar Observatory. There's many observations of the sunspots are made. Sunspots have been observed from Kodaikanal for hundreds of years, for 100 years or more. They appear dark. They are cooler than the photosphere. They're actually not very cool. The photosphere has a temperature of about 5,000 degrees Celsius. Sunspots are a mere 3,000 degrees Celsius. So they appear much darker than the background photosphere that they are in. There are areas where there are strong magnetic fields. If you have a magnet on your refrigerator at home, that's maybe half a Gauss. The sunspot magnetic field strengths can be as much as 4,000 or 5,000 Gauss. Very, very strong. And they're also gigantic. Several Earths would fit inside this particular sunspot. The number of the spots that is on the surface of the sun changes from a minimum to a maximum and back, and takes about 11 years to go through the entire cycle. Sometimes it's as short as, say, 9 years, sometimes it's as long as 14 years, and the sunspots have also, we know, have vanished for a while also. They are the cause of solar flares, coronal mass ejections, and space weather. So this is where space weather comes from on the surface of the sun. Sunspots have been known for a very long time now. They were first observed, as far as we can tell, back in 800 BC in China and Korea. In fact, down here is sorry, how do I go back? Oh, they got it, thank you. This is an old Chinese painting which shows the sun with some sunspots on it. In 1128 AD, a monk in England, John of Worcester, actually made the first Western picture of a sunspot, it's shown here. And then in 1600, when the telescope was first invented, there was a sudden explosion of information about sunspots. Kepler saw them, but he thought it was Mercury. The person who actually discovered them is the man named Harriot. The Fabricius father and son pair, Shiner, all observed sunspots, and then Galileo came along and he observed them as well. These are all various pictures, various drawings that those astronomers from the early 1600s made. So one of the things they noticed, though, was that the spots were moving. And particularly these three guys, Fabricius, Shiner, and Galileo, saw the spots were moving, and they figured out that the sun has to be rotating in that case. So here we have a number of, at the top, we have a number of drawings by Galileo on 4 different dates, and you can see the pattern of sunspots has moved across the disk at an angle in this case. Shiner was the man who did most of the early work, and this is one of his pictures of how the sunspot move. And this is Fabricius' original paper, the first paper that actually mentioned this back in 1611. So we've known that the sun rotates for a very long time. But the sun rotates not the way you know the Earth rotates. The Earth rotates as a solid body. In other words, the length of a day in Udaipur is 24 hours. You go up to the North Pole, the length of the day is still 24 hours. Not so on the sun. On the sun, the period of rotation depends on what is your latitude. So the equator of the sun rotates with a period of 25 of our Earth days, and it increases as you go up towards the pole of the sun until here it's about 35, 36 days. So how can the sun get away with this is because it's not a solid rock like we are living on, but it is a big ball of gas or plasma that is electrically charged, so it is free to do that. This was actually noticed by Shiner that it was differentially rotating, but it took till the middle of the 19th century for Richard Carrington to actually very carefully observe and determine a number of things about the sun's rotation, particularly the angle of its axis to the plane of the solar system, as well as these actual periods as it goes through. So this is a very key thing, this differential rotation of the sun. This is a picture, this is my only equation, so don't panic. This is the equation that tells you the rotation rate of the surface of the sun as a function of latitude phi here. This is a plot of it here. The latitude, the equator is at this end down here where it's about 24 in a few days. And then you see it's not a straight line. It goes up to about 34 in a bit days as you get up towards about 80 degrees latitude. So it has this sort of functional form of a sine squared and a sine to the fourth, and these are the actual coefficients of the equation here. So about 15 degrees per day at the equator is how much the sun rotates. How do we do this? How do we know this? How do we measure the surface rotation? Well, we've used tracers where we look at sunspots and we carefully measure their position throughout time. We can also use other aspects of the sun, granulation, network, and we do cross correlations of images or maps of the magnetic field, and you get these sort of plots here that are all they're very similar in shape, but they also have some slight differences. And there's been a lot of discussion as to why those differences occur. Depends on maybe the depth at which these features are actually anchored, or other effects of the characteristics of the photosphere in which they're measured. A better way of doing this is to actually use spectra of the lines, and particularly the Doppler effect on spectral lines. Now, The Doppler effect is something you've all experienced when an ambulance or or a police car goes by. When it comes towards you, it's a very high pitch, and as it passes you, it drops to a lower pitch. So that's the Doppler effect. Things that emit waves that are moving towards you have shorter wavelengths. As they move away from you, they have longer wavelengths. It works for sound, it works for light as well. So you've probably heard of the redshifts for galaxies. Those are moving away from us by quite a bit. We can, on the sun, we can use the same thing. Here is this is a pretty little chunk of the spectrum of the sun. These black lines are what are called absorption lines of various elements, and you can see that they are jagged. They are not nice smooth lines. That jagged part is the Doppler shift. This little stuff, this little area here is moving towards you, and this little area over here is moving away from you as you go along in position. The amount that this line shifts is a measure of the actual velocity of that particular area. So we use this actually to measure all the motions of the solar surface, not just the rotation, but a lot of the other measures, a lot of the other motions as well. So why does it do this? Why does it rotate differentially? Well, this is not an easy, this is still have some questions about it. It's a complex interaction. There's the convection coming up. There's the Coriolis force, which is a force due to the rotation of bodies on the Earth. If you fire an artillery shell north, well, it gets deflected towards east or west, depending on which hemisphere you're in. So we have that interaction, and we have the magnetic field itself. The convection is a movement of mass outward, perpendicular to the rotation axis due to the steep temperature gradients. As I said before, it starts about 70% from the core to the surface, and the Coriolis force is then pushing that mass parallel to the rotation axis. So this interaction of these two forces carries some of the angular momentum of the sun, and it redistributes the angular velocity throughout it. The motions of the charged particles, plasma, the electrical charged particles that the sun is made out of, a moving electric particle creates a magnetic field. And so that is another whole area of complexity that provides a type of friction or viscosity that essentially links the whole system together. Now, the details of how it ends up with the particular rotation rate and all that are still, shall we say, under discussion. But that's the basic physical picture of why it does this in the first place. So now I'm going to talk a little bit about the solar cycle. As I mentioned, the number of sunspots varies over about 11 years or so. It's not a strict, very precise time. Like I say, it could be longer or shorter. During that, after every 11-year cycle, the overall solar magnetic field flips its polarity from if in one cycle the North Pole is a positive polarity. As you may recall, magnets have positive and negative polarities, similar polarities that repulse each other, opposite polarities attract. So in one cycle, the north, say, will be positive and the south will be negative. In the next cycle, it's going to be reversed, with the north being negative and the south being positive. At solar minimum, there are hardly any sunspots visible on the solar surface. At solar maximum, there are lots. So that's the key thing about it. But why does it do all this? Again, it's differential rotation that plays a major role. This is a plot down here of the solar cycle over 400 years. I said there was a time when they vanished. That was called the Maunder minimum down here. It was shortly after they were first detected. They all seemed to disappear. However, we now know that even though the sunspot disappeared, the solar cycle did not. The magnetic cycle was still going on, and we know that by looking at historic records or geological records of carbon-14 and other fission products that are in the Earth's atmosphere and carbon material. But since then, since about the middle of the the 18th century, the sunspot cycle has been going along tickety boom, as my colleagues in Britain would say. And we are now in cycle number 25, counted back to the first one in around 1750. Now, the magnetic field is buoyant and rises to the surface. So the sunspots then emerge, and they emerge in a particular pattern that's called the butterfly. Here we have cycles going back through down to looks like 1800. Our current one is here on the right side. This is actually cycle 24, so this doesn't quite get into cycle 25. See the distinctive pattern. The sunspots emerge at about 30 degrees latitude, and then as the cycle goes on, they emerge at lower and lower latitudes throughout the course of the solar cycle. This is called the butterfly diagram because it looks sort of like butterfly wings. And it's a major aspect of the sunspot cycle that needs to be understood. So the sunspots, as I said, are areas of magnetic fields. These days in solar physics, we create many images of the solar magnetic field, such as this one called the magnetogram. Again, this is a minimum. The surface magnetic field hardly there. Gray is about 0. On this picture, black is strong positive polarity. White is strong negative polarity. So here you see sunspots, very strong sunspots here, and very strong sunspots below the equator as well. The total magnetic field is also higher, of course, during solar cycle maximum. So where does that come from? Where does this magnetic field come from in the sun? Well, this has been a topic of research for, I don't know, 50 years easily. Still being debated in many details, and I'm going to give you one picture, which is in broad brushes, probably okay. Don't quote me on the details because I'm sure somebody will argue with them. But let's start over on the left side here. And these lines here are the magnetic field of the sun, and there's the differential rotation going on. So if you start with magnetic fields that are parallel to the rotation axis, because the equator is rotating faster than the poles, it winds them up. It winds them up around the entire sun as years go by. So after that happens for a while, then when the magnetic field is strong enough, as I said, it gets buoyant, it rises like a cork in water and starts to protrude on of the sun, and that's your sunspots. Those are the sunspots that we were looking at here. Then they protrude, and then they break, they reconnect into a different pattern. They form these sort of cells. There is another motion inside the sun that transport these fields back up towards the poles. There's a couple of mechanisms for how that happens, and then after 11 years, you're back to having this original structure of magnetic fields parallel to the rotation axis, and then you start all over again. That's the basic idea. This all requires differential rotation to happen. No differential rotation, this does not happen. So basically, sunspots and the solar cycle exist because the sun rotates differentially, which is one of the reasons we are very interested in the rotation of the sun's behavior. This is a picture of the magnetic field on the surface over the solar cycle. Again, these are areas of the sunspots here. They are coded in 2 different colors for polarity. Blue is a negative polarity, yellow is a positive polarity, and you can see a striking variation in the polarity of the fields here. Here in this cycle, the northern hemisphere was all positive sunspots, and the southern hemisphere was negative. It's actually not the sunspots themselves, but the way the polarity is distributed within them. But then you see that there's the movement of the magnetic field back towards the surface, back towards the poles of the sun, as shown in those diagrams there. For the next cycle, everything flips its sense. So then there's a polar field up here, and then it flips its sense, its polarity, and off you are onto the next cycle. So, but now what about what's going on inside the sun? So we know that it's not rigid. We knew that from a long time ago. So there was a lot of speculation about what the inside was doing. And it's very critical for dynamo theories that we know this. The first idea was that angular momentum is conserved inside the sun. Now, what's angular momentum? If you watch your figure skating, you see figure skaters who twirl with their arms out. And when they bring their arms in, they twirl a lot faster. That's because they are conserving angular momentum. So if you're spinning and you have your weight out here, you have a certain amount of angular momentum that is conserved. So if you bring it in here, to conserve that, you have to spin faster. So people thought, well, that's reasonable. That's what the sun might be doing, right? So that means that you would get lines of constant rotation. This is the solar rotation axis. You would get lines that would be parallel to the solar rotation axis. It was called constant cylinders. You would get this sort of pattern of rotation inside the sun. There was one big problem with this, and that's the poles should rotate faster than the equator in that case, and not slower. So there was clearly something wrong with that particular idea. But that was basically it in terms of what people thought for many times. But then something called helioseismology came along. And helioseismology was started when in 1960, the solar surface was observed to go up and down with a period of about 5 minutes. And this is because there's sound waves all throughout the solar interior. You can think of the sun as a gigantic musical instrument. It's filled with sound. It rings like a bell. It has millions of notes of global modes of oscillation. A piano has 88 keys, 88 notes. The sun has 5 million. If we measure those frequencies very precisely, we can then infer what the inside conditions of the sun are like, including velocity and rotation. Here's a little bit of the language of helioseismology. We talk about P modes that are pressure modes, acoustic modes, with G modes, which are the restoring forces, internal gravity and buoyancy. There's the fundamental F mode, which is the breathing mode of the sun. There's the whole sun going in and out like this. We can see P modes and F modes, but we cannot see the G modes. The G modes are very deeply buried and do not seem to make it up to the surface for us to see them. There's, like I said, there's 5 million global P modes. They're described by something called a function called a spherical harmonic, which are identified by 3 quantities known as L, M, and N. Those 3 letters. This is a picture of how the waves travel inside the sun. We have here P modes. Some of them are confined near the surface. Some of them go deeper down. Some of them go all the way through the core. And then when they hit the surface, that's where we can observe them. Here's another set of P modes here. And this is G modes here on the right. They are, as you can see, are trapped very deeply inside the sun and cannot have not yet been unambiguously observed at the surface, though people have claimed that they have, but no one really thinks that they have yet. We really would like to see the G modes. This is a picture of some of the spherical harmonic functions. The waves form on the surface of the sun. We have the number L is called the spherical harmonic degree, is the number of nodal lines on the surface, the number of these planes that actually cut the surface of the sun. So here is L equals 6 with 6 planes. M is the number of these planes that are perpendicular to the equator. So you could have none, you could have all of them, or you could have something in between. So you get patterns that are either like this, or like that, or like a checkerboard almost. And these are just low order ones. Here's some examples of other ones that we observe. As you go to higher and higher values of L, you get a more and more intricate checkerboard pattern. This also shows you the third number, N, which goes inward. We do not observe that on the sun, on the surface of the sun, but we tell what that is by the frequencies. So this is a picture of of all the frequencies of the sun, given what we think is its structure inside. The P modes are the set of these lines up here. Um, the G modes are the set of these lines down here. And this is a function of the spherical harmonic degree or the wavelength that's on the surface of the sun. And this is the y-axis is the temporal frequency, and that's how we separate the values of n. The F mode is this one line that goes right down, separating the P modes and G modes, and goes through both of them essentially. So how do we do helioseismology? Well, Gong and other helioseismic instruments, every minute they take a picture of the velocities on the surface of the sun. We then remove the rotation of the surface of the sun and all other fields like convection, granulation, and supergranulation. And on the far left, you'll see a yellow speckled thing. All that's left are the velocity fields of the oscillations. We then multiply that picture by a whole bunch of these pictures of spherical harmonics. We do it for every minute, and then we add it up over the entire surface of the sun, and that gives us 1 minute of amplitude of that particular spherical harmonic. And so this then is a time series for a certain spherical harmonic of that particular pattern on the surface. Then we stack all those up. We take a power spectrum, and you get this. This is an observed spectrum of the acoustic waves on the sun. Each one of these ridges corresponds to a different value of n going in the surface, going into the interior of the sun. This is a temporal frequency on the y-axis, and the spherical harmonic degree or wavelength on the x-axis. Now we have a number of ways to look at this guy. Look at this spectrum. Here we've taken a little slice, and we're looking at it in great detail. We have very low L. You can see that these spikes are evenly spaced. That has to do with the structure of the sun or the star. Here we've blown up an even smaller portion, and you can see that there's a lot of structure there. And that's due to the fact that the waves are being excited randomly, stochastically. So their phase keeps getting reset all the time. You can go back and you can enlarge the spectrum I showed you the previous slide. It really breaks up into a whole bunch of smaller ridges. Again, each one of these, a lot of these are artifacts actually, because we cannot actually see the entire, all 360-degree surface of the sun. So we have, when we go to get one particular spherical harmonic pattern, we actually have nearby others bleeding in to our results. And here's a real close-up. This is what the rotation does to the oscillations. This is how we can measure the rotation from helioseismology. You see that this is tilted. You can see that this is reminiscent of that picture I showed you earlier of the rotation rate on the surface. The curvature at the ends comes from differential rotation. We get one of these for many, many, many different modes of oscillation. And because they all sample different depths, we can disentangle all that and measure the internal rotation as a function of depth. That is what helioseismology does for us for solar rotation. There's another way to do this in addition where you use areas across the surface instead of the entire surface of the sun, and then you slice the power spectrum in a different manner, and you get these rings. If you have a flow under the ring, it moves them depending again on what depth they sample. So we can then get the subsurface velocities and rotation below small areas, not only just globally on the sun. So this is what the rotation of the sun is really like. This is what helioseismology has told us. It's really different from what people expected. At the surface, here on the left we have a cut through the sun. The surface is this line up here. The core is right down here. We have color-coded the rotation rate. Red is fast, blue is slower. This is the equator. This is the pole up here. And what we see is a differential rotation actually persists all the way through the convection zone. However, right below the convection zone, it disappears. It turns into solid body rotation, completely unexpected. Here now we have plots of the actual rotation rate at the equator, 0 degrees, 15 degrees latitude, 30, 45, 60, and 75. So here is where they all converge at this rate of about 430 nanohertz at the bottom of the convection zone. So all these different rates converge right there. You also see that there is a sort of a surface layer here, very near the surface, where the rotation rate increases and then starts to decrease on the way down. So this was unexpected, but this is what helioseismology says is happening inside the sun. There's a very curious thing about this plot. There is one latitude shown by this green line where the rotation rate of the surface matches the rotation rate of solid body below the convection zone. That's shown by this green line here. It's a little bit more than 30 degrees. It's a little bit more than 30 degrees. So the surface, like this particular latitude, is directly connected to the rotation rate of the interior. Now take a look at where the sunspots start to emerge. This is the same latitude. So one might think that the magnetic field that creates the sunspots somehow is not disrupted by the differential rotation and manages to work its way up along this direction to be seen at the surface at the beginning of the cycle. And then other things happen to it to change it. So this transition at the bottom has been labeled the tachocline, completely unexpected. It's where you go from differential rotation to a solid body. There's a very strong velocity shear. That means that velocity changes quickly over a relatively short range of depths. It could be a place where the solar magnetic field is actually generated. It's very thin, which is a big puzzle. It's only 5% of the solar radius. It seems to be thicker near the poles. We think that it may be confined, that there may actually be a small fossil field, fossil field within the radiative zone here that is helping maintain the solid body rotation and the tachocline. Here's a plot of the tachocline on the left that shows you the thickness of it, and you can see that it is thicker at the higher latitudes. And this is a picture of the temporal variation of the rotation rate across the tachocline over 30 years of observations. So it clearly has a time variation, which may or may not be solar cycle dependent. So it's still a very active region of research. We still don't quite understand how it is formed. There's lots of theories about it. And of course, nobody has quite the right answer yet. Near the surface is also a near surface shear layer, again, where the velocity changes quickly as a function of depth. Here you actually do get some conservation of angular momentum near the surface. It's very thin. We also again see very substantial solar cycle variations, and sunspots may actually form here instead of deep down in the tachocline. There's some relatively new papers out about how that might occur. So basically, we don't know where the sunspots form. They might be deep down, they might be up near the surface. The jury is still out and the arguments are still raging away. So that tells you a little bit about the rotation through the convection zone and the radiative interior. What about the core? Down way at the bottom where the nuclear fusion is taking place? Well, the core, some people think the core rotates a lot faster, like 4 times faster than the surface. Some people think it rotates about the same speed as the surface. It's hard to measure this because not very many of those P modes go all the way down through the core. This is why we want G modes, because they are in the core, and if we could observe G modes clearly, we would know. But we don't. They're not detectable because they cannot really travel through the convection zone. Currently, there's an effort going on now, led by Kiran Jain, actually, from Udaipur, to use through all the observations we have, the process to PMOS to see if can we actually get any better than this. Jury is out, we'll see. Another aspect of rotation is something called the torsional oscillation. If you take away the surface rotation, you average it out and remove it, you get this very distinctive jet stream pattern. You see these red chevrons, which are higher than average rotation rate, and in between are lower than average rotation rates. And you can see they move, that zone seems to move down towards the equator. And in fact, this is highly correlated with the progress of the solar cycle. You can actually determine the timings of the solar cycle by the slopes of these lines. You can say when the cycle will actually begin fairly clearly by when it crosses a latitude of about, what do you know, about 33 degrees. You can also see that there's increased rotation that goes towards the poles or decreased rotation that alternates, again, in correspondence to the magnetic field moving that way. And one interesting thing about this plot, this is cycle 23, which was 22 years ago. This is cycle 24, 11 years ago. This is the one we're in now, cycle 25. And here is the next cycle appearing. So we already know that cycle 26 is coming. There it is appearing in the torsional oscillation. We'll be keeping an eye on that as time goes on. Now that brings me to the poles of the sun. You might notice that all those other plots kind of stop. There's a hole near the poles. That's because we can't see them very well from the Earth. So what's happening with rotation at the poles? Well, if you look at gas giant planets like Jupiter and Saturn, they have this really distinctive, crazy patterns at the poles. You see vortices, little tornadoes everywhere. There's actually sort of a hexagonal structure on Saturn and all that. I mean, a lot of interesting stuff. So what's happening at the sun? Well, we just now have solar orbiter that is just now reaching a place where we can actually see the poles. So here it is, and it looks just like the rest of the sun. So you don't see those tornadoes, those hexagonal structures. I mean, if those lines were not there, you would not be able to tell that wasn't somewhere else on the sun. So that's a clue, I mean, as to what's happening. Now, the sun rotates a lot slower than those gas giants. So the Coriolis force is a lot lower here, for instance. And soon we will have helioseismology at the poles using solar orbiters, so we will be able to see what the solar rotation is below the poles in addition. But right now, it looks pretty much like it's going to be the same as it is everywhere else. This is brand new. There's something called inertial modes. There's a back and forth sloshing. As you can see, this red and blue here that occurs up near the poles. Very hard to see this. We needed 10 years of data to actually detect these things. They have extremely low frequencies, periods of over 100 days, but they are certainly there. They're there when you do all the data reduction. Doesn't matter which instrument you're using, you can see them. They have, for instance, a very low frequency of 86 nanohertz, which is about 115 days. So that's a brand new thing that we're just now beginning to exploit for our knowledge of the sun. So that concludes the portion about what we know about solar rotation and how we know it. Now, I'm going to change the direction a little bit and tell you some of the aspects that the solar rotation occurs on the sun that are important to us. There's space weather. I imagine you've all heard about space weather on TV. Sunspots can change up very abruptly. They create a flare. You've heard of probably X-class flares, which are very energetic. They can initiate coronal mass ejections, where the sun basically barfs up into the interplanetary space. There's usually more events at solar maximum, though they can occur at minimum too, and they can affect technology. One of the biggest events we know of happened way back in 1859. That man Carrington, who was doing the rotation, detected a very strong flare. It disrupted the new technology at the time, telegraphs, took them offline. Some of the equipment got so hot that there was fires were started in the telegraph offices in Britain. Auroras, space weather causes auroras, the northern lights. The auroras were visible way down, way south in the New Mexico, US, for instance. Luckily for us, we have a magnetic field on the Earth and we have an atmosphere. And that protects us from a lot of the damage that's done by space weather. But it can still affect us. And solar rotation is because solar rotation causes a solar cycle, causes the sunspots, causes the flares. Solar rotation is the basic cause of space weather. So this is a schematic of what the space weather is like. There's the sun over there on the left. You saw that picture earlier. The solar wind, which is material that's always being ejected from the sun, it has gusts in it called CMEs. The photons and the charged particles, the photons make it over to the Earth first in about 8 minutes. The charged particles take 3-4 days, depending on how fast they're moving. But then they hit us. They hit the Earth. The Earth has a magnetic field around it called the magnetosphere. The solar wind particles can find their way into the magnetosphere through these regions, and this is where the aurora are formed, where the magnetic field of the Earth actually connects down into the surface at higher latitudes. So in Norway, Sweden, and things like that, that's where you can frequently see the aurora. And the Earth's atmosphere also protects us from these electrical particles that are coming. However, it can do a lot to us. These are some of the technological problems that occur due to space weather. So your coronal mass ejection or cosmic rays. Astronauts are at risk for being exposed to radiation. Satellites can be damaged, destroyed. Their systems disrupted, so they go out of control. Also, satellite drag increases with solar activity, so they are brought to Earth more quickly. When the charged particles hit a layer of the Earth's atmosphere called the ionosphere, which is electrically charged, well, that disrupts our radio communications because our radio communications typically travel through there and bounce off of that. In addition, GPS signals. Disrupting the ionosphere, you're disrupting the GPS signals. So if your self-driving cars are not going to be happy during solar maximum, because if they depend on GPS, they're going to have errors of maybe 3 meters or 5 meters, and that's not good for a car. That's a lot. Airplanes lose communications. Crews and passengers are exposed to radiation from space weather. You get the radios, this scintillation in the radios. The radios can go out. And in fact, it's because of this stuff that we got very interested, and particularly the US Air Force got very interested in solar physics during World War II, because we were getting all sorts of disruptions. Was it the enemy? No, it was the sun. And that was the beginning of solar physics research, particularly of interest by the Air Force. So you get this disturbed reception. Here's some aurora down here. Your navigation can go off, your boats don't know where they are. I've seen a great picture of a tractor with GPS, nice straight GPS lines, and then the solar flare effects and all the roads go off because they suddenly lost their GPS. And if it's really strong, you'll induce electric currents in the surface of the Earth, in the crust, and that'll be picked up by power systems, power grids, and in extreme cases, the power systems will fail. This happened in 1989 in Quebec, and this arguably is the worst possible thing that could happen because transformers, the power systems use huge transformers, and those transformers can be destroyed by solar activity. And those transformers take years to rebuild. So you could lose power over a wide range for years because of solar activity. Very extreme case, unlikely, but it could happen. It's one of the reasons we worry about space weather. So that's sort of a reason of why the solar rotation is important for space weather. Now, turning to something a little different, habitability of exoplanets. We live on a nice planet. What do we need for life? We need a nice stable surface. We need the right temperature, not too hot, not too cold. We need liquid water. We need an atmosphere with oxygen. This is all as we know it. And we now know we need a magnetic field because we need not too much ultraviolet, not too much X-ray, because those wavelengths of light can first erode the planet's atmosphere. This happened to Mars because its gravity was not enough to hold on to the atmosphere, and it can destroy life itself without that. So the activity level of the central star in your stellar system is crucial, and so is the magnetic field of the planet. So you have to have a planet with a magnetic field and an atmosphere and a not too active star in order to have life. So we're still learning about all the aspects of this. Here is lots of the minimum planetary magnetic field. So you have a planet with a magnetic field. What do you need to be protected from stars of various activities, various sizes, and various rotation rates to be protected? And to show you how there's room for research here, folks, if you want to do research, this is the Earth here. Well, it is below the minimum activity level of the sun in this model. So according to this plot, we should be toast, but we're not. So something's clearly wrong, and there's some research here to fix up these plots in particular to understand them. Now we can determine the activity of distant stars. We have done this by looking at the stellar ultraviolet emission from other stars other than the sun. And we have seen many stars which show nice cycles. Some stars show no cycles here. Some stars show some sort of variation, but not really a cycle. Here's some more examples. And here's a star that had nice cycle going, and then stopped, like a Wonder minimum or something like that. So we can obviously determine the activity level and how long that activity cycle is by that. We can also get the stellar rotation rate. We can do the same thing to stars we can do to the sun with seismology. We can't go very high in degree, but we can certainly see low degree oscillations, and the spacing of these peaks and then the spacing of these little peaks tell us about the structure of the star and the rotation rate of the star as well. So we can actually measure the rotation rate of many, many stars now that we could not do before. So then we can look at the relationship between rotation on the x-axis, the period, how fast the star rotates, so 20 days, 30 days, 40 days, 50 days, and how long that activity cycle is. And there are two branches that we see, this red branch and this blue branch. We use something called the Rossby number, which is simply the ratio of the period of the star to how fast the convection is turning over inside, but that requires a model to get. If you have a small Rossby number, that means you have rotation dominating and pretty much have high activity. The opposite for a large Rossby number. So we have these two branches. Notice that the sun actually doesn't sit on either of them. And there's a puzzle here because what you have over here is a short cycle and high activity. So that would imply a small rotation rate, a small Rossby number, and a small rotation rate. And the opposite here, but it's completely backwards, again, from what the Rossby number suggests. More research opportunities here, folks, to figure out what this is doing. It also affects stellar evolution. These complicated pictures over here are how a star evolves in terms of its surface temperature and its brightness as it goes through its billion years of lifetime for various masses. And this is with rotation, without rotation, and you can see that the plots are different. So you need to know, again, what the rotation of the star is like in order to get this right. This is another picture of how that, what the initial mass of the star will be what the final mass will be with respect to the initial mass. And you can see again, the rotation rate makes a big difference here. Stars will lose mass because of these stellar winds that are coming out of them. So, okay. So conclusions here. Why do we care about the rotation of the sun? It's really important for a number of reasons. It creates sunspots. It's a basic cause of the solar activity in the solar cycle. It creates space weather, which can ruin your cell phone reception and other things. Your airplane navigation, radio communications, and extreme effects. It can have impact the habitability of exoplanets. So you have to, if you're looking for exoplanets, you have to worry about that. And it affects the stars. So there's very many reasons about the rotation. Now, I just want to say at the end here a few words about, this is the Arvind Bhatnagar Memorial Lecture. This is Arvind here with his wife. As you know, Arvind founded the observatory back in 1975. In 1990, we was selected as one of the Global Oscillation Network Group sites. And GONG is one of the systems that has provided the helioseismology that has revealed what the interior rotation of the sun is like. So thanks to that, USO is a very important factor in our understanding of the rotation of the sun. And also thanks to this excellent management by USO and PRL, USO is going to be part of the next generation of GONG, which is now currently in development, funded by the National Science Foundation. This is probably this is the current concept of what it's going to look like. So you know that big white box up there is going to be replaced by, I guess there's two big white boxes, sorry, and a pier, most likely. The pier will probably be something like 5 to 8 meters in height. There'll be a light feed up at the top. Some of the sites are going to have a coronagraph, but I'm afraid not Udaipur. It's a little too misty here. But this is now all in development. The NG GONG will be the same 6 sites, have a lot more instrumentation in it. It won't just do helioseismology, it's going to do space weather forecasting as well, and designed to do that. And USO future will be part of the NG GONG. So thank you, everybody, for all your attention during this, I just made it, this lengthy talk. And let me know if there's any questions.
Thank you very much, Ram, for nice information shared.
A lot of it.
We have a wide range of audience attending this talk. We have students and faculty from university and colleges in Udaipur who are attending here in person. Then we have PRL Ahmedabad colleagues and IA Bangalore colleagues attending the talk on WebEx as well as on YouTube. So first, I would like to have few questions from the audience sitting here.
That's
in
fine.
USO. So please, okay.
What G mode? What about it? So a G mode is a global mode of oscillation of the sun, and instead of a P mode, a pressure mode, the restoring force is pressure, acoustic. And a G mode is buoyancy, gravity. That's why it's called G mode. So it's because there's a density gradient of density inside the sun, and that gradient actually produces a motion. So it can sustain waves that move through that area where there's not any convection, and then it will reflect off again the bottom of the convection zone, form standing waves or standing modes of oscillation. But they're all trapped below the convection zone, and they cannot penetrate through the convection zone to the surface where we would observe them. So we're pretty sure they have to be there, but we so far have been unable to detect them. Does that help?
Hello, sir. Thank you for the talk. So my question is, as the Earth's rotation is
Sorry, you have to repeat. Period of our, the Earth's rotation? Sorry, I'm still, the sun is not, no, it's not. I mean, uh, the sun's rotation rate, um, overall is staying constant, as is the Earth, except for very small variations. I mean, the Earth is slowing down because of tidal effects and things like that. As far as we know, the sun is not. But there's so much other activity, so many other velocity fields that are occurring on the sun that it's not out of the realm of possibility. And the sun will be will actually be slowly changing its rotation rate because it's losing mass. The stellar wind is being emitted all the time, and that will change the rotation rate of the sun as well, but over millions of years, very slowly. Again, you'll have to help me. Sunquakes. Oh, well, that's what helioseismology does. Helioseismology is the study of those sunquakes, basically. So on the Earth, we have something called seismology, where when an earthquake goes off, waves travel through the inside of the sun. I'm sorry, inside the Earth, and they are detected somewhere else. And by studying those, we learn about the stuff they move through. We do the same thing with the sun, only instead of occasional earthquakes, it's doing it all the time. There's continual sunquakes, if you would. And that's what's generating the P modes that we observe for helioseismology. So we have shall we say, borrowed many of the techniques of the terrestrial seismologists for our work in the sun. So it's for a single earthquake, it has a lot more energy than a single P mode, but there's a lot of P modes. And so we add them up all together, they're a lot more than an earthquake. So sure. Yes. Yes. Uh, doesn't look like, there is a slight hemispheric asymmetry. Um, but I do not think that it has really any effect on the solar cycle at this point, know of. So
Thank you. I will move another call there. Students sitting in the
yes,
ask if there are questions.
that sounds fine. I understand. That's okay. It's a lot of information. That's a concept, It may, who knows if it'll actually look like that when it's all done. To get above the boundary layer, we're gonna have 2K by 2K cameras and we want better seeing. So we're trying to get above the boundary layer. There's a boundary layer of bad seeing. Yeah. Right, ground heating and all that, right. 50 centimeters, 50. Yeah, now it's like 10. So yeah, it'll be a lot bigger. Yep. Hi. So you'll have to repeat that, please. Still didn't quite get it. What did you? One person at a time. Yes. Yeah. Repeat it like. Got it. All right. Thank you very much. Plasma, plasma is electrically charged gas. So the gas, the air we breathe is normal gas. In a flame that glows, that is a plasma. The temperature is so high that electrons have been stripped off the atoms of the, and so they're electrically charged. So that's what a plasma is. It's electrically charged gas. TV, your TV plasma monitors. This is not the same plasma that's in your blood, by the way. Not that plasma. That's still a liquid. But it's, and it's very because of moving electric charge makes a magnetic field, which then feeds back onto the motion of the electrical charge that made it in the first place. It's a very complicated physical problem to study what the dynamics are of a plasma, of a charged gas.
So now over to Rajan, because we have colleagues online from here in Ahmedabad and I Bangalore, as well as on YouTube. So those questions will be taken by Rajan.
वो आपको अनशेयर करना है चेंज मोड में Hello. Anyone from the people who joined the WebEx platform? I mean, questions from the people from the. Hello, can you hear me?
Hello, am I audible?
Yes.
Yes. Yes. Dr. Hill, first of all, thank you for this wonderful talk. I know in terms of talking about the solar radiation, space weather, and exoplanets, I think you touched a lot of ground there. I was, curious to know about this NG, next generation, facility. Could you tell us more about that? Like, what is it? What is going to be? How is it going to be different? And what's the instruments are there in that?
Right, right. It will be a follow-on to GONG. It will continue to do helioseismology and will have spectropolarimeters in it to do magnetic field. We are planning on doing many, many different spectral lines. These are still being chosen now as the instrumentation is in development. There's an IR spectrograph, a spectropolarimeter, Doppler imager for helioseismology, a sun is a star seismometer, and there will be a couple coronagraph at 3 of the 6 sites. It'll be the first time we have a coronal network.
Okay.
All these instruments, the whole system is now in development. It's just starting. We were awarded a 3-year contract from the National Science Foundation to develop all the instruments, the idea of the instruments and the sites and the plans of the whole thing. Then we will submit a construction proposal at the end of those 3 years, and then presumably get the money to go ahead and build it. So it's quite a ways off. There's going to be 3 years, 3 years of development, and then probably at least another 3 to 5 years of construction before it's up and running. But it'll be GONG with the same sort of measurements, but with many more spectral lines and much better measurements of magnetic fields.
Okay, thanks for that and for that information. But in the schematic that you showed, at least the diagram, I think it looked like a big tower with a with a human size there, just to
Right, yep.
scale.
Yeah.
So why is that? So that's not clear to me. Like, why is that required?
Right, we are, the spatial resolution of the current gong is 2 arcsecond pixels, 1,000 by 1,000 across the sun. We're going to be going to double that to 2K by 2K, so 1 arcsecond per pixel. So seeing the turbulence has become an issue. And one way you can reduce that is by raising your instrument and your light feed as high as feasible above the turbulent boundary layer that's the first 5 to 10 meters off the ground. So it's a relatively inexpensive way of, improving the scene. There may be adaptive optics eventually as well. That's the other way that people are doing it. But even so, it helps to get to get the light feed up in the air.
Okay. So how is it different than putting it in a tall building?
Not very different. You do have to, a tall building also can create seeing itself. Uh, um, and it really isn't that much different. You could put it into a tall building with instrumentation around it also.
Okay.
I mean, for instance, the DKIST is something like 30 meters in the air.
Okay.
So, but that gets to be very expensive then. So there's a fine line between feasibility and
Yeah.
performance.
Thank you. Thank you for this information and all the best. Best
Thank you,
wishes
sir.
for that. Yes. Thank you.
USO will be part of it.
Yes. Thank you very much.
Okay, anyone else? Any other question? Okay, there is one question from Sandeep Dubey. What are the spectral lines you are planning to observe with NGCOM? Spectral lines that you are planning to have with NGCOM?
Yeah, not specified yet. That's one of the things that's going to be chosen during the development phase. Because we have spectral polarimeters, we basically have the entire spectrum open. We will, of course, have to choose a few lines to concentrate on and do regularly. But that's one of the things that has to be determined during the development is exactly which those are. So we do not know yet.
Okay. Yeah. Anyone else from WebEx platform? Okay.
There is one question here in the audience.
Okay. Yeah.
What is the 11-year solar cycle and what's happened during that cycle?
Say it again, sorry. The youngest?
He's asking about the 11-year solar cycle.
How short? They've been observed to be between 9 years and about 14. That's the usual range. Is that what you're asking? What is the range of length of the cycles? Yes, short is 9, long is 14.
No, he's asking
Oh.
about why the cycle is there in the sun.
If you can answer that, congratulations. It has something to do with the rotation of the sun. We think that there's this interaction between the rotation and the magnetic field and the Coriolis force and many other things. But as I said, the details are completely unknown in a way. They've been argued about for decades, and I don't think the argument is over yet. So it's basically unknown what the real basic detail mechanism is.
Okay. Since there are no other questions from the WebEx platform as well from YouTube, so I'll hand over the mic to Brijesh.
Yes. So thanks, Raja. And this brings us to the concluding session of the 112th episode of the PRL Ka Amrit Vyakhan series and the fifth Dr. Arvind Bhatnagar Memorial Lecture of USO PRL. So first of all, I would like to thank Dr. Frank Hill for accepting our invitation and giving this excellent talk on as the plasma turns, the rotation of the sun, highlighting the importance of studying the sun and the ongoing GONG program and the future NGE GONG program of NSO. This is essentially serving the global solar community to deeply understand the fundamental processes that occur on the sun and the solar activity, which has great societal impact. It is a pleasure to mention here that the Udaipur Solar Observatory of PRL has been a part of the international program GONG of NSO since its inception in the year 1995, and this was possible due to the efforts of Dr. Arvind Bhatnagar. Thanks again to Dr. Frank Hill for nicely answering the questions from the audience, as well as sitting in USO, WebEx, and YouTube. At the same time, I would like to express my sincere thanks to Professor Anila Bhardwaj, Director PRL, Professor Pallamaraju, Dean PRL, and Professor Shivu Matthew, Head USO, for their continuous support in successfully organizing the talks in this lecture series. Thanks again to the committee members of PRL Kamrit Vyakhan and Dr. Bhatnagar Memorial Lecture series for their efforts for smoothly organizing the talks in this series. Thanks again to all of you for being with us in this lecture. And with this, these words, I propose the closure of today's session. See you again in the next PRL Ka Amrit Vyakhan series. And I think we have something to hand. Okay. That's fine. Thank you very much, everybody. And now we will close the session here.